MIT Motorsports is a student team which competes in a competition called Formula SAE or FSAE. Our car competes in a series of dynamic events or races. Although our car isn't driverless, we can still definitely benefit from developing control algorithms for some of the simpler events. One of these events is the skid pad event, which is a figure 8 to test steady state lateral acceleration. That's the event that I wanted to make a controller for this project. I developed a controller that regulates the vehicle to the steady state cornering equilibrium using LQR and trajectory planning in Drake. I used a pretty simple model. I just used a bicycle model with linear tires. So linear tires means that an increased slip angle or slip ratio always results in increased force in either the lateral or longitudinal direction, depending on which of those slip quantities you're talking about. In real life, tires have a maximum amount that they will produce force and a maximum slip. Beyond that slip, you start getting reduced force. I don't account for that explicitly in the dynamics, but I do have a check against the maximum slip angle in the cornering equilibrium calculation, and I also have constraints for that in the trajectory planner. The inputs to the system are the slip ratios at the front and the rear tires, as well as the steering angle. And then to track the position of the vehicle in space, the state includes in polar coordinates
radius, radial velocity, angular velocity, and the heading with respect to the theta hat vector of the vehicle and the drift that angle. In this notation, that angle is called phi.
The one piece of position and pose that's not included in the state vector is theta itself, because as you go through uniform circular motion, your theta is going to be changing, but everything else will remain constant.
We can get these equations of motion through force and moment balance, and then we can find the rest of our steady state values by solving for them using the ones that we specify.
In this project, I used two different types of control. I experimented with infinite horizon LQR and finite horizon LQR stabilizing around a trajectory generated using direct collocation. Infinite horizon LQR can maintain the cornering equilibrium pretty well, as you would expect. You know, when you start at the equilibrium, you stay at the equilibrium. And it can also tolerate reasonably large deviations in the initial conditions, but not a huge amount. This table summarizes how well it responds to disturbances in the different state variables, and these were about as big as I could get without the vehicle diverging into some other arbitrary trajectory, so I just got these by playing around with different initial conditions. To try to expand the range of initial conditions that the vehicle could recover from, I tried introducing a trajectory planning element. So that's where I used direct collocation to generate some trajectory that starts in whatever initial conditions and ends at the equilibrium position, and then uses finite horizon LQR to get there. And then once the horizon of that finite horizon LQR is reached, that's when the steady state infinite horizon LQR controller takes over again. Overall, the trajectories generated were usually pretty erratic, and I think this is because it's getting stuck in some local minimum because the dynamics are nonlinear. Overall, I would not say that this trajectory planner is really reliable. In terms of next steps, I did do some tuning of the Q and R matrices, but I think that they could be improved by more tuning. In terms of modeling, like I said, this project uses a pretty simple model, so there's a lot of ways in which it could be improved. You know, it doesn't include load transfer even in the longitudinal direction, which you hypothetically can do with a bicycle model. Obviously, with a bicycle model, there isn't really a lateral direction for load to transfer, so it doesn't account for lateral load transfer. The tire model is linear, and something like the Pesheshka model would be more accurate, but that would also introduce a pretty non-linear element. I think it would actually be interesting to try to use some piecewise model and try to come up with a mode schedule. Overall, I'm pretty satisfied with how at least the infinite horizon LQR controller was working. I'm definitely interested in continuing to mess with this simulation and try and maybe implement some of these other changes.